Last time we talked about super translations, and our subject for this time is superrotations. But let me first review a few things from last time. So we were studying asymptotically flat metrics in classical and quantum gravity. And they start at leading order at large R. One has just these terms, minus 2 du dr plus 2 r squared gamma z z bar dz dz bar. These terms are just the flat Minkowski metric. And then we come to the corrections, which are 2m Bondi over r du squared. That's the leading correction that you get if you, say, just have a black hole. And then there's the term that comes from gravitational waves, rcz dz squared plus r c z bar dz bar squared. But today we're going to need, and then we also wrote down the term dz czz du dz plus dz bar cz bar z bar du dz bar. But there are more corrections to this metric, and there's more and more physics in the subleading terms. And so today we're going to be interested in a subleading term. And the subleading term is a correction to du dz. We have 1 over r nz, 4/3 nz minus 1/4 dz of czz czz du dz, and plus the complex conjugate of this involving nz bar. Now, this term here, so I could have just called this whole thing nz. There are various different conventions in the literature. In other words, I could have just defined the coefficient, the 1 over, so this, the term we've been discussing is an order 1 coefficient of the du dz term. This is an order 1 over r coefficient. And I could have just defined the whole thing to be nz. There are different definitions in the literature. This 4/3 looks kind of funny, but it makes some subsequent, and this shift by this quadratic term in C also looks kind of funny, but it makes some of the subsequent formula simpler. This thing has a name. It's called, so this is called the, as I said, it's called the Bondi mass aspect. The function of u, z, and z bar. And this is called the angular momentum aspect. So far we haven't talked about angular momentum. And roughly speaking, the standard ADM formula for angular momentum involves this nz in the same way that the ADM formula for the energy involves and momentum involves mz. Okay, so this is an important thing. And if we want to, in fact, let me write this. I was going to do this a little later, but let me write it here. This is not a new piece of data, but it's constrained by the constraint equations. So remember, we said that before that in order to get, if you knew the news, the bounding news, the u derivative of C, you had to specify a boundary condition on C to integrate it to get C. That boundary data is part of what CZ is. It's a coordinate on the phase space of outgoing classical field configurations. And then you integrate that, and the constraint equation, once you have C, completely determines M. Well, at least in the situations that we're considering, we're demanding that M go to 0 at Scri++. Now, there's a constraint equation for N. And the constraint equation for N is, so that's the GUU. So this is determined by GUU equals the matter UUU times 8 pi g. And this one will be determined by GUZ. And the GUZ constraint equation is du and z. So it's like the Bondi mass aspect in that it's determined by a constraint, is equal to 1/4 dz dz squared czz minus dz bar squared cz bar z bar. And this bit turns out to be related to a component of the Weil tensor, plus dz mb minus tuz, where tuz is defined as the limit as r goes to infinity of r squared times the matter uz plus a term which can be thought of. So tuz is a moment. It's not the energy density. It's the momentum density in the z direction. And so TUZ, so there's a gravitational contribution to TUZ, which is, where did it go here? Yeah, minus 1/4 dz czz nzz minus 1/2 czz dz nzz. So this can be thought of as the momentum density of the gravitational field. As in the matter field TUZ, if we had a scalar field, it would be du phi dz phi. And here we have terms going like du on C and dz on C. Okay. All right, so I was going to review last time, but I got a little ahead of myself there. So let me continue on what we discussed last time. So we took this metric here, and those are the leading terms. and it defines a certain fall off, or we demand a certain fall off. And then we looked for vector fields which are bounded in a local orthonormal frame as we go to future null infinity, and preserve this form of the metric without necessarily leaving CZZ and all these other terms invariant. And we found that these are the famous super translations, zeta f, generated by vector fields f du minus 1 over r dzf dz plus dz bar f dz bar plus dz dz f dr. Yeah. And so this changes the field. In particular, the most interesting piece, if we take the Lie derivative with respect to zeta f and act on the metric and see what the resulting CZZ is, we get it's what you would expect, which is f du CZZ. But then there's a funny term, inhomogeneous term, minus 2 dz squared f. So we could say the usual vacuum in some coordinates might be where you just have the top line there. That would be Minkowski vacuum. But if we do a coordinate transformation on that, we still have something which is completely vanishing Riemann tensor. But CZZ is no longer 0. So this symmetry is spontaneously broken because some components of the metric transform inhomogeneously under it. This top form of the metric is not invariant. And we also know that it's not a pure diffeomorphism. One way that we know that is because we wrote down the charges that generate this symmetry. And 1 over 4 pi g gamma zz bar f times the bonding mass, and that is equal to an analogous charge evaluated on square minus. So just the fact that the charges are non-zero and conserved means that these are not trivial. These charges are coordinate invariant, so something coordinate invariant is changing under these super translations. And moreover, we gave some examples where it's clear that you can delay something on the North Pole and not on the South Pole. And it's clear that if you perform these super translations, you're changing the physical configuration, even at the classical level. And then we went on to assert, so we could write this charge, use Gauss's law and the constraint for M, the GUU constraint. We could write it as an integral over all of Scry, and then it had a soft piece and a hard piece. The soft piece created was linear in the gravitational field. Zero momentum created a soft graviton, and then there was a hard piece which gave us various intricate numerical factors acting on the outgoing states, acting on the outgoing ingoing states, and writing those as quantum, promoting it all to the quantum level, we led to the Ward identity S QF minus n is equal to 0, which is one relationship for every function on the sphere. And and then I didn't show, but it was similar to the QED case, though more indices, similar to the QED case, to show that after 5 or 10 pages of algebra, if you don't make any mistakes, that this turns into the Weinberg soft graviton theorem in its conventional form, which let me write down because I might want to compare to it later, which is basically that out A minus S, so we annihilate a soft graviton. Let me not look up the factors, but it has this Weinberg soft factor of the sum. So we have a negatively polarized graviton, epsilon mu nu, sum over all ingoing and outgoing particles, p mu k, p nu k over q dot pk times the same out S in without the soft graviton insertion. Okay. So the lesson here is that, and then there was also a discussion about how we can't, BMS didn't really have a symmetry. They just had an action on the Hilbert space. They didn't understand that something commuted with the Hamiltonian or the S matrix. And we were able to show with these subtle antipodal boundary conditions that there is a kind of diagonal subgroup of the BMS acting on the future and the BMS acting on the past, which is in fact a symmetry of both of classical quantum gravity, of classical gravity, we showed directly, and then in quantum gravity it follows from the soft graviton theorem. Okay, so that's the summary from last time of the super translations. Let me ask if there's any questions before I go on. Okay, so we made a very big assumption when we did this, or not assumption, a restriction, that that the components of zeta, we wanted to preserve these boundary conditions, but we wanted to demand that the components of zeta be bounded in an orthonormal frame as we go up to scribe plus or down to scribe minus. That's clearly too strong an assumption because it rules out both Lorentz transformations and rotations, which clearly should be included in our list of symmetries of Minkowski space. So one can do, and BMS did do, the analysis without that assumption. And I'm not going to go through the whole story, but I'm going to explain the important pieces of it. So let's start with the formula zeta y is equal to 1 plus u over 2r yz dz, and I'm going to, along the way, my goal is to show how the Lorentz transformations generalize to the so-called superrotations. Yz dz minus u over 2r dz bar dz yz dz bar minus a half u plus r dz yz dr plus u over 2 dz yz du. So the claim is that if we're, and in fact this is a homework problem, that if we're in Minkowski space, namely we just have those top three, that top line there, that if we take yz to be 1z or z squared, and plus complex conjugate. If we take yz to be any one of these three numbers, and times possibly a phase, then that gives us 6 generators, 6 real generators, and those 6 real generators are the boosts and rotations. So for example, let's consider yz equals I times z. Then we have this becomes 1 plus u over 2r I times z dz minus z bar dz bar. And yeah, and all the rest of these terms vanish because divergence of y is 0. They cancel with the complex conjugate. And so actually maybe this one cancels with this. Yeah, I think this one is going to cancel with that one. So so in this case, we just have, that would be rotations, phase rotations about the z-axis. And in fact, if we look at infinity, we get yz dz. If we look at what this vector field reduces to at r equals infinity, it's just y dz dz plus u over 2 dz yz du. So what is that u doing there? Well, let's draw a picture of Minkowski space. So when we add in the complex conjugate, this becomes divergence of y, which I'll write as divergence of y. And we get a plus yz bar dz bar. Now divergence of y is the rotations are killing vectors on the sphere, and so their divergence vanishes. But divergence of y will not vanish if there's some boost involved. And so what do boosts do? Well, boosts preserve these hyperboloids that look like this. So the action of a boost is on scribe plus is a vector field which goes like this and gets bigger and bigger as you go to u equals plus infinity or minus infinity. Same thing over here. So the boosts, the boosts map the hyperboloids to themselves. So they do something like this. And this is this is the limit of one of the hyperboloids, and so we get mapped along null infinity like that, and if divergence of y will typically have a maximum at one point on the sphere, where it will be positive, and it has to integrate to 0, of course, and a minimum at the other side will be negative. So be moving the north pole up like this, and moving the south pole down like this. Okay, but, and it leaves fixed the light cone of the origin, so this point doesn't get moved. But nevertheless, it does become singular at infinity. Okay. Now, what happens, now let's think for a minute about what happens if we take if we compute for a general yz, not necessarily one of these three. I want to compute the formula for the Lie derivative with respect to zeta y, which I'll denote Lie y, of the components of the metric. So it turns out that Lie derivative with respect to y of GUR is order 1 over r squared for any vector field y. Lie derivative of y of GZR is, well, order 1 over r. And Lie derivative with respect to y of GZZ bar is order r. But the important one is Lie derivative with respect to y of GZZ, which is equal to 2r squared gamma zz bar dz yz bar. So this is the important equation. And this equation was derived in 1962 by Bondi, Metzner, and Sachs. And this says that basically that yz bar is a holomorphic function on the sphere. And so you might say, okay, so yz could be 1 z squared, which we already talked about. But what about z cubed, or z to the 4th? The reason they didn't consider those is that if you go to, of course, the z coordinates don't cover the whole sphere. They don't cover the, if z equals 0 is the north pole, they don't cover the south pole. And if you do the coordinate transformation to the south pole, to the other pole, you'll find that z cubed is becoming singular. So these are what's called the 6 global conformal killing vectors. And so that's what they said. They said we only want to consider diffeomorphisms which are finite at infinity, and so we're going to throw all of these guys out. And now, this same equation was encountered 20 years later by Belov and Polyakov and Zamolodchikov and other people around that time when they were developing the theory of two-dimensional conformal field theory. They found that two-dimensional conformal field theories typically had a symmetry group generated by vector fields like this. And so they said yz bar can be any meromorphic function on the sphere. Now, if yz bar is 1 over z bar minus w bar. Then dz yz bar will be equal to 2 pi delta squared z minus w. So you can't have this be 0 everywhere on the sphere. Now, in standard textbook treatments of conformal field theory, why are you allowed to do this in why does one do this in two-dimensional conformal field theory? The symmetry is when these things are 0, yet if yz bar is just a meromorphic function, and if it's just one of the infinite dimensional, all the conformal killing vectors, not one of the global things, then it won't quite be true that this vanishes. So when BMS saw this, they said, okay, we're throwing out all these guys. We're just going to keep these 6. But when BPZ saw it, they said, well, let's keep the whole thing. Now, why is it okay in two-dimensional conformal field theory? Well, if you ask people whose life's work is two-dimensional conformal field theory, is to do conformal field theory, they'll all give a different answer. And I would say that my answer would be that one of the answers you might hear a lot is, if we're only studying physics in some local region, why do we care if there's singularities in our symmetry transformations somewhere else? Well, there might be a reason that we would care. I don't know. It might contribute. But so you get different answers to this question, and you can go look up your favorite conformal field theory textbook and see what they say about it. But I think the real proof of the pudding, this, of course, the symmetry that's generated in two-dimensional conformal field theory, it's the most studied infinite dimensional symmetry group that there is. It's called the Virasoro group. And why is it interesting? I would say the reason it's why we should do it is because we use it, we derive identities that relate some correlation functions to other correlation functions, and we know we can show algorithmically that those identities are correct identities. So it's good to talk about this as a symmetry because it gives identities, concrete identities among correlation functions. That would be my sort of practical view of it, that it's good for something. Now, so various people, so the question is, so what BMS did was they just took the global ones, and then they constructed what they called the BMS, was later called the Bms Group, and that's a semi-direct product of the Lorentz group with the supertranslation group. And it's important to note that in that, even before we go to this infinite dimensional group, that in that semi-direct product, there's no preferred, it's not a direct product, it's a semi-direct product, there's no preferred Lorentz subgroup. There is an ideal in the group, which is the translations, so energy and momentum are well defined, but there's no preferred subgroup that you can call, there's no preferred SU2 subgroup that you can call angular momentum. This is referred to as the problem of angular momentum in general relativity, but it's not a problem, it's just how general relativity is. That's just not, there's this infinity of charges. But now various people have made this suggestion that that we should as was done in two-dimensional conformal field theory, we should go beyond the 6 global conformal killing vectors and consider the whole infinite dimensional group, which is called the superrotations, and they comprise the Euclidean Virasoro group acting on the sphere. So that, of course, is a very interesting conjecture because we've learned an incredible amount about the fixed points of two-dimensional field theories just from the properties of this conformal group, and to learn that 4-dimensional quantum gravity transforms under exactly the same infinite dimensional group is surely going to be an extremely powerful thing in understanding its properties. Now, I first learned about this conjecture in some papers of Barnick and Troussert about 5 years ago, who worked out a lot of the details of how all these things transform. They have some very long papers, which is why I didn't assign any of them. They're important papers, but they're long ones, and they have a lot of formulas, and they do things in great generality, and they're not easy to read. Yes, Derek?
Is there a central extension in the algebra that generated?
Of course, this is Virasoro algebra.
So what does that see?
Right. So another interesting thing about this superrotation group is that there have been very few papers written on it. And there clearly is a central charge, as you'll see in a minute, but exactly how it's defined and what the proper normalization hasn't been worked out yet. But I'm pretty sure that will happen within the next year or something like that. So there are a lot of very nice papers, which I found very helpful, by Barnick and Troussert, but they're very long papers that are just with all kinds of details in them, all about the classical structure of how all these coefficients transform under the superrotations. Then I discovered that there was a footnote in a paper by Tom Banks about 4 years earlier, in which he was a paper on something completely different, in which he clearly made the statement that one should allow all the conformal killing vectors. And then after that, I discovered a paper by De Boer and Saludkin, which is a very nice paper to read, and it's one of the assignments, which I think will provide a lot of groundwork for future work on the subject, who arrived at this group from a different point of view. They looked at a hyperbolic slicing of Minkowski space and were using analogies to ADS-CFT. They were driven by how you should adapt ADS-CFT to Minkowski space, and I think many of the things that were conjectures in their paper have now been proven. And then I realized that actually there's some obscure papers by Penrose, including in his Twister newsletter, that he actually knew a lot of this also. So it's an idea which has been sort of floating around there in various forms. But certainly Barnick and Troussert were the ones that brought it to everybody's attention. But as I'm going to say, at this point, at that point up until recently, and I'll talk about this in a moment, we still didn't know the answer to the question of whether or not these things should be allowed. And the way I'm going to propose that the answer should be the question should be answered is we need to have some concrete relationship between S matrix element. In other words, there better be some new soft theorem that this is related to. So that's where we're going. Any more questions? Okay, great. So now we can start working out. And again, the best reference for these formulas are Barnick and Troussart. We can start looking at Lie derivatives of CZZ. And when I write d dot y, I mean d dot y is equal to dzyz plus dz bar yz bar is equal to u over 2 d dot y nzz plus y dot d czz minus a half d dot y czz plus 2 dzyz czz minus u dz cubed yz. And then delta y nzz we get by taking the u derivative of this, and we get u over 2 d dot y du nzz plus y dot d nzz plus 2 dzyz nzz minus dz cubed yz. Okay, so if we're at u equals 0, or if we're looking at some zero mode of n that doesn't depend on u, these last two terms here are exactly the infinitesimal transformation law of a stress tensor in two-dimensional conformal field theory. This is the linearization of the Schwarzian. So so some mode of n is going to be related to the stress tensor. Okay, so now what we want to do is to talk about the quantum theory. And in the quantum theory, I'm going to assume that we have a symmetry, and that this thing generates a symmetry. And then I'm going to, from that, get a soft theorem, and then one can use diagrammatics to prove the soft theorem. Okay, so we define the charge q plus y on some out state. We could talk about in states or out states. I'm going to talk about outs. Is the operator that generates this delta y. So we know what delta y does. Here it is. So we need some operator that generates this on the out states. And that is obviously going to have a hard part and a soft part. And what is the hard part? Well, so suppose we are labeling, we have some set of particles, Z1, Z2. It should be equal to minus I. So the hard part will act on the individual hard particles, where by hard I mean not at zero momentum. So the hard part will be one term for each particle, and it should be yz at the point zk dz. So this is going to all act on z1, z2. So there'll be k z1 to zn. There'll be n terms z1 up to zn. K equals 1 to n. d dzk. That is because so these are at infinity. So if I go up all the way up to infinity, it just acts as yz d by dz. Right? So that's just the first term in zeta y. Right? So I want to move the position of the particle by zeta y. And then I have the second term, actually the last term. So on scribe plus, I didn't write this down, I guess, or I wrote it down and then I erased it, that if I look at the action on scribe plus, this just reduces to zeta y is equal to yz dz plus u over 2 d dot y du. And in fact, to keep the writing down now, I am going to just complexify, and I'm going to just write it down for one component of y. So let me just call this dz There should also be a yz bar, dz bar, but I'm just too tiresome to write all that. So I'm just going to complexify the transformation and just have a yz. OK, so I need to generate that term. Now d by du is I times the energy, and u d by du is the same as it's d log u, which is d log energy. So I get another term, which is minus ek over 2 dz yz at zk d dek. So these particles, I'm suppressing it, but they also have an energy. OK, so that's how the hard part has to act in order to implement this Lie derivative. Now, so what is the operator that would do that? Well, the operator that would do that is Q hard plus is equal to 1 over 8 pi g integral over scribe plus du d squared z yz bar tuz plus dz yz bar u tuu. maybe I didn't need to rewrite it in terms of E. Maybe it's easier to see that U d by du is generated by U TUU. So TUU is the operator that generates translations in T, and integral of TUZ is the thing that generates translations in Z on Scry. So whereas before, with the super translations, we were just moving the sphere up and down. But now we're doing something rather different. If we're looking at, suppose YZ is YZ bar. I've lowered an index. If I raise the index back up, I have YZTUZ. That's generating a translation Z d by dz. In other words, it's generating a rotation about the point z equals 0. So these things are generating rotations on the sphere, but they're not global rotations. They're position-dependent rotations on the sphere. So this is the operator that would generate that. And what about the soft piece? Well, to get the soft piece, we use the fact that the soft piece should have the property that its commutator with NZZ is equal to I dz cubed yz, right? Because the commutator of the total Q with n has to give us this. And the only way it's going to give us this is an inhomogeneous term. This isn't an operator. These other terms are linear in n. So in order to get a term like this, we need to have a term in the charge which is linear in the fields. That's going to be the soft term, right? So now we know what the commutation relations are. It's just free field theory up on Scry+, and one finds NZZ NWW bar. Same calculation that you did with the symplectic form for electromagnetism, except there's twice as many indices, is equal to 16 pi I times Newton's constant times delta squared z minus w times du delta u minus u prime, where this guy is at u and this guy is at u prime. OK, so we need to find the operator that does that, given this. That's not a very tall order. One finds then that Q S plus is equal to minus 1 over 16 pi g du d squared z dz cubed yz u n z z bar. Okay, so you take this, you commute it with an n. That will give you, this will collapse this into a delta function, but then you have a delta prime here, so that will kill this u here, and you'll just be left with dz cubed yz, which is the term that we needed over here. Any questions?
So why in the commutator between n we assume there is a partial u of the delta function? Usually for free field
We don't assume that. We compute that. But it would be like that for, I mean, if you had a free field du phi on a null surface, du phi with d prime phi will go like du delta u minus u prime delta squared z minus w. It has to by antisymmetry.
Oh, so n is like the momenta.
N is the u derivative of c.
Right.
So n with c has no du here. C with c is kind of non-local. It has a theta function. Okay, so, but this isn't an assumption. This is derived in any number of papers, and there's also what else could it be? All right. So now something very nice happens, which is if we define q plus y, and quite non-trivially. So now several highly non-trivial things are going to fall together in a row. But maybe we should take our 5-minute break. Let's take our 5-minute break. Okay, so now let's look at the quantity q plus y, which we're going to take as an integral. All these integrals were over scribe plus. But now let's do an integral over scribe plus minus. I'm going to put a 1 over 8 pi g here. D squared z, yz bar, nz minus u dzmb. Now, the first thing that might bother you about this expression is that we're evaluating it at scribe plus minus, where u is minus infinity. However, if you look at the GUZ constraint equation, if we go to u near u equals minus infinity and we assume we're talking about some finite energy configuration, near scribe plus minus, TUZ must be 0. And this turns out to be related to a component of the Weil tensor, a curvature invariant. And so this will also go to 0. So we have that du and z is equal to, so if we assume that the bonding mass goes to some constant function at scribe plus minus, remember generically, the bonding mass, of course, the integrals of it weighted by f are the supercharges. And generically, the bonding mass is some completely random function. And so dz of the bonding mass is not going to be 0. I mean, it's 0 for Schwarzschild or something, but it's not even 0 for Kerr. If you put Kerr in bonding coordinates, which turns out to be a rather difficult thing to do, but if you put Kerr into, Barnick and Trousseau do it, into bonding, but only at leading order at large r, then dzmb will be non-zero. And so du nz must diverge like dzmb at infinity. In other words, nz must grow in such a way so that the leading u behavior of this cancels, and we're just left with the finite piece of nz. Okay, so this is a finite expression, and indeed we had something like this in the fermionic charges where there was some linear and u term, but everything canceled. And in fact, if we take yz bar to be one of the, sorry, one more thing I want to say. In the first problem set, when I had you solve for box epsilon equals 0, where epsilon was an arbitrary function on the sphere at infinity that was U independent, one found that the subleading term necessarily in the 1 over R expansion necessarily had a U divergence. And so this phenomena of subleading terms having linear behavior in U and diverging at U goes to plus and minus infinity is ubiquitous, and this is another, albeit more complicated, example of it. So when I say that you need to pick NZ, the initial data for NZ, when you solve the constraint equation, in fact, once you have the bonding mass, the linear in U term is determined, but there's still a finite piece left over that is an integration constant that you need to specify. So if we want to determine a physical geometry, we have to give more information. And interestingly, I'm not completely clear if it's understood. I know that I don't understand exactly what the situation is at higher orders, and if you want to be able to solve to all orders in the 1 over R expansion, if you get new integration constants at every order, or if, I suspect not, I suspect that it stops at some order, but I don't actually know how it works or know of anywhere that problem has been spelled out. In fact, even in electromagnetism, I'm not sure how it works. Okay, now if we take YZ bar to be a Lorentz transformation, then this expression has been written down before. Well, we would add the complex conjugate, and this is just the 3 angular momenta and the 3 boost charges. So the boost charges are sort of like, what are the boost charges? I guess if you're just in particle mechanics, the boost charges are PIT minus EXI. So that's what they work out to be. If you take a particle stress energy and contract it with the Killing vector. So if you take the time derivative of this, I guess I need a, yeah, okay, this must be the non-relativistic version of it. EXIK. Wait, this isn't quite right. All right, let me not try to sort that out in real time. But it's something, but the boost charge is something like that. All right, so now the beautiful thing that happens is I take this expression and I can integrate by parts. So of course it's equal to 1 over 8 pi g integral over scribe plus d squared z du yz bar, and then I have du nz minus dz mb when I hit that u, and then minus dz of du mb, but du mb is something like d squared of n plus or minus TUU. That's the GUU constraint equation. And now if we take this and plug this in, And we just get exactly this term plus this term. So we can see, these had a u in front of them, sorry. So we can see roughly where some of these terms are coming from. Here we see in Q hard we have a term u t u u times dz yz bar. We take this, we integrate by parts, and we get a dz yz bar u times t u u. Not going to try to match all the numbers here, but they do all match. So that's one of the hard terms. The other hard term obviously comes when we take du nz, which has a tuz on the right-hand side. And so we just get a tuz with yz bar. And then the tedious part is there's some soft terms which are here, and then there's also more soft terms which come, by soft terms I mean terms linear in the gravitational field, and those all combine to give exactly this, except of course it will be integrated by parts. The dz's will all be acting on the ends. So that's a somewhat tedious calculation, but it works. So I might have proceeded a little differently in this discussion, different ways of approaching this. I might have said, okay, in classical GR, this should be antipodally matched, and therefore we have a conservation law, and but that's a little harder to do because well, it's a finite piece that you're subtracting out some u divergence, and you have to worry about various kinds of ambiguities. So probably could have been set up that way. But instead what I did is said, okay, let's, now if this is all true, so if these superrotations are really a symmetry of gravity, then the real proof of the pudding, as in two-dimensional conformal field theory, is that in two-dimensional conformal field theory, we talk about there's relationships between correlation functions that are implied by the Virasoro symmetry. Similarly, there should be relationships between S-matrix elements, which we have all along been arguing should be viewed as correlation functions on a sphere. And are those relationships actually true? So now we can look at Q plus Y, S minus S, Q minus Y, out in. And we can work that out very explicitly because we know exactly what all these operators are. And now, and we can turn it into momentum space. Now, this isn't how the calculation was actually done, but in principle, one could do it this way, which is we've learned the tricks for writing Q's and P's in terms of Q's and PK's in terms of Z's and ZK's in transcribing this. Here we're starting with the Z's. So we infer from the location Z the momentum of each particle, and we have its energy and so on. And what one finds after quite a lengthy calculation is that, though it wasn't done in this order, I'll say in a minute how it was done. That we have Zn plus 1, Zn plus 2. So we have some outstates like this. And then we take A minus of Q, the annihilation operator for a negative helicity graviton, S matrix Z1 to Zn. So what is this 1 plus omega d omega doing here? Well, let me write the whole expression out, and then I'll describe it. It's equal to S1 minus Zn plus 1, Zn plus 2, dot, 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 S Z1, Z2, where S1 minus is equal to minus I, sum over all particles K, Pk mu, epsilon minus mu nu, Q lambda, Jk lambda nu over Pk dot Q, where Jk lambda nu is equal to the sum of the orbital angular momentum and the helicity sk lambda nu of internal spin of the particle. Okay, so let me say some words about this formula. So first of all, in general, when we insert a soft graviton, we get a pole of something proportional to 1 over omega. That's what we saw in the super translations, the Weinberg pole. But this 1 plus omega d omega projects out that pole, right? Because omega d omega times 1 over omega is just minus 1. So it's minus 1 acting on the pole. And this is plus, oh, we're taking omega to 0, sorry. Now, Q is equal to omega times 1 Q hat. And so it says that the subleading term, we already had a soft theorem for the pole, but now we're projecting out the pole and looking at the finite piece. This formula says that there's a universal term, a universal form applied, a universal form that must be true for every quantum theory of gravity, at least semi-classically. If these are really good symmetries. So up to now, the jury has been out about whether these singularities were really going to prevent this at the poles, would somehow mean that this shouldn't really be thought of as a symmetry. But if we have actual relationships between S matrix elements of this type, then we can say that It's a symmetry. So then, after deriving this, so Cacciazzo and I showed by some diagrammatics, Feynman diagrammatics, that at tree level, by an argument that was many, many times more involved and tedious than what Weinberg did, that this subleading, that there is such a subleading soft theorem in gravity. So this is an example where now we're really starting to learn something new. When we were talking about QED, we were saying things everybody knew in a new language. But now now we're learning something new. There was a conjectured symmetry of gravity. If that symmetry were really to be a good symmetry, there would have to be a soft theorem. This is the soft theorem that it would have to be. And then you can check diagrammatically that this soft theorem is true to all orders in tree-level perturbation theory. Okay, now, so that demonstrates, in other words, I suppose you could now run the argument backwards. Since we proved the soft theorem, it can be run backwards, and we see that these superrotations are indeed a symmetry of semi-classical gravity. Now, an important check on this. Well, let me say another word about the form of this. Notice that this soft factor. Sorry, one important thing about this soft factor is notice now that we have a q on the top and a q on the bottom. So this, as we take omega to 0, this remains finite. So indeed, this limit as omega goes to 0 is good. Comparing to what we did with the soft theorem with super translations, this q lambda j lambda nu was replaced by p nu. Okay? And that makes a lot of sense, because if we look at the hard terms here, ignoring this somewhat confusing terms for a moment, but just looking at this simple term here, we're replacing, in this usual soft theorem, we would just have f times TUU, but now we have TUZ times this vector field z, so we're generating a rotation around the axis which the particle is emerging through. So, and you can make this more precise if you look at details of, and this is how I guess this formula. If you look at details of geodesics with non-zero angular momentum and what their TUZ looks like, you can see that replacing f TUU with f with TUZ YZ is like replacing p mu with q contracted with the angular momentum, and the q there is to give, it's the direction around which the rotation is being performed. Anyway, once you, that argument can be made more precise, but the way that one knows that the guess must be right is that if you look at this formula, you can ask, remember one of the important consistency checked on the Weinberg soft graviton theorem was that it didn't change if you take let me just remind you, we had sum over k epsilon mu nu pk nu over pk dot q. And so if we write epsilon mu nu is equal to lambda mu q nu, in other words, a pure gauge graviton, the soft factor should vanish, and indeed it does become lambda mu sum of pk mu, and then q dot p k over q dot pk. So these terms cancel, and this is 0 by energy momentum conservation. So now let's look what happens to this expression. Well, if we shift this expression, we get S is equal to this S1 minus, let's forget the minus, we can take any polarization. We get sum pk mu, and now it's not automatically symmetric, so let me put both terms in. Lambda mu q nu plus q mu lambda nu, and then j k rho nu q rho over pk dot q. So we have two terms here. This one is going to vanish just because Q is antisymmetric. J is antisymmetric. So if we contract it with two Q's, we get 0. So this one vanishes. And here we have a P dot Q, which cancels this P dot Q. So the whole thing becomes equal to lambda nu q rho sum over k jk nu rho, which is equal to 0 by overall angular momentum conservation. So overall angular momentum conservation is to this subleading soft theorem, and I'm not sure I introduced this word. It's called a subleading soft theorem because it's not the leading term as the graviton momentum goes to 0. It's the subleading term. And so angular momentum conservation is to the subleading soft theorem what energy momentum conservation is to the leading soft theorem. And this is actually how it was worked out. It wasn't sort of, if you just start from this expression and try to go into momentum space, you're going to get all kinds of terms and you're going to be confused about what should and shouldn't cancel. The way it actually worked was this formula was kind of guessed based on the combination of this argument about angular momentum flux through local angular momentum flux to infinity replacing momentum flux through infinity, and the fact that this seems to be the unique formula that has this property that it vanishes for pure gauge gravitons. And then once you know what to look for, it becomes much easier to show that these statements are equivalent. Okay, so let me now make some comments about this. First of all, there's a similar, we haven't talked about it, but there's also a subleading soft theorem in gauge theory, in abelian gauge theory, which was discovered in 1958, and it's related to some symmetry that we don't really understand very well now. It gets loop corrections. In gravity, there is a subleading soft theorem, and it also obeys. It also is, the term. So the first three terms are universal in gravity, and the third term also vanishes for things like this, but it doesn't involve a conservation law. It's more like this first term. It just involves contractions of some symmetric object, antisymmetric object with 2 powers of q. Same thing is true with the subleading soft theorem in QED. It's not related to some global conservation law that we're familiar with. Another important thing about the subleading soft theorem in gravity, which is related to is equivalent to the statement of superrotation invariance, is that known is maybe too strong a word because people set up their calculations in a different way, but there seem to be corrections at one loop and only at one loop, and we don't understand what that means, whether it's an anomaly in the symmetry or it means one has to make loop corrections to the transformation laws, or it's just a subject which hasn't been explored. And in fact, there's a similar issue in non-abelian gauge theories where the leading soft theorem has corrections which occur at one loop, or only one loop. Okay, but the main thing conclusion I want to draw from this is that it appears that 4-dimensional quantum gravity has at least at tree level and with some one-loop corrections whose form we don't understand, has the transformation laws of a 2-dimensional conformal field theory. And those transformations laws have been extraordinarily powerful in understanding things about the structure of two-dimensional critical theories, and we would like to apply similar reasoning to understand things about 4D quantum gravity. But we should not expect, I think it won't be the same story. We don't know exactly what kind of representations are appearing. We don't know highest weight, lowest weight. We don't know what sort of norm we should be using. It's all sort of a blank slate at this point because this is new and there's been very little work done on it so far. So I think I'm actually that's kind of a natural stopping point. So I think I'll stop there and just, Shuhong had a question.
So are all these soft vectors, leading, subleading, sub-subleading, are they all homomorphic? You write it in terms of the
You mean in spinor variables?
No, just in terms of the z coordinates. The z that pointed in the direction of S2.
So in the so in the gauge theory case, one writes we constructed a current, which we called the soft photon current, which had holomorphic poles and generated the the gauge symmetry. Here, there should be a stress tensor. I think I know what the formula is, but it's not, there should be a similar, some operator that, is related basically to the ends and integrals of ends and so on, whose insertion in S matrix element obeys all the Ward identities of a two-dimensional field theory.
But what about the subleading term in the gauge theory? Is the soft factor there a holomorphic function of Z, or it also depends on Z bar?
I think there's probably also a current there.
Oh, okay.
Yeah.
And then for the Graviton case, so the leading soft Graviton theorem, the soft factor.
But I don't think that's been worked out carefully.
Of the subleading soft factor in gauge theory?
I don't think we tried to construct the current. I think there is a current, but I don't think we tried
But
to.
wouldn't you just interpret it as the non-singular term in the JOOPE?
Well, you have to say what J is.
I thought it's the sen J that we put in for the leading soft factor.
No, it won't be the same J. It's a different.
Oh.
It's a different object.
Right.
I mean, one thing you can see here, if you look here at the soft part, the soft charge here, this U is sort of crucial. So there was no U in the leading soft graviton theorem. So this was a U derivative. So we just got the difference between the NZZ, CZZ at the top and CZZ at the bottom. With the U in there, it's a different story. You can still write this in terms of graviton creation and annihilation operators, which is what we did, and that's how we got this formula here. But it's a different kind of construction. I mean, I think all these questions you're asking are answerable. They just have not yet been answered.
So for the leading soft graviton theorem, the soft factor still looks like a 1 over Z divergence, right, in some sense?
The collinear divergence is 1 over Z minus W.
Right, so it's not a 1 over Z squared in particular. But wouldn't we expect the TOOPE to start with 1 over Z squared? Or are we saying that the weight is actually 0? If we try
Well, maybe, but first we have to construct T, and that hasn't been done yet.
Yes, but I'm just saying that from the soft graviton theorem.
Well, so T hasn't been constructed yet. I mean, I think it's definitely I'm sure it's a solvable problem. It's a different question whether the answer will be useful. But the appearance of this term is strongly suggestive that there's some kind of central charge floating around somewhere. But in order to say what that is, one must first construct T, and then show that it finds something that has the right OPEs, and then normalize it correctly, and then get the central charge.
Do you have a feeling that you can have both the holomorphic T and the anti-holomorphic T at the same time?
No, it'll probably be like, I mean, I would. Well, yeah, that's a good question. Yeah, I don't know. I was about to say I'd expect it to be like the gauge theory, but But in the gauge theory, you have this, it comes about because double soft limits don't commute. And I'm not sure that that is true in gravity. Gravity has less infrared divergences, though it does have this pole. It might be similar. Okay, if there's no more questions, let's stop there.